those of you that don't know me, I'm Jamie. I work in Patrick's team at J&J, and I spend a lot of time developing cohort diagnostics. So this talk is going to be on the kind of technical side of how you actually run cohort diagnostics, and then Azza will give you more of a background and description of how you actually go about using a Shiny tool to understand cohorts. So, the objective is to familiarize you with the package, show you that it's not that scary to actually run code, kind of explain how you can do phenotype development iteratively, which is one of the crucial aspects of this work, is that, we can't really show it here, but you tend to gather information about what your phenotype algorithm does and then try and adjust your phenotype accordingly. And then kind of provide links to resources. This is going to be somewhat code heavy. However, everything in this this slide deck is designed to be copy and paste, apart from any of your internal CDM settings. So, you don't have to think too much about this. We don't expect you to share any results that you generate in this part of the SOS challenge. That will be kind of captured in a future tutorial that Anthony Senna will be giving. Sorry. So firstly, like an overview of the package. So I would argue that developing good phenotypes is not the most complicated necessarily part of a study, but it is one of the most crucial, because if you don't capture outcomes correctly, then how can you be sure that any effect estimate or any prediction that you make from your study is reasonable or valid? And this is kind of crucial, even more so because there's not really a standard devised in the community outside of what we do for objectively determining if a phenotype is good. So, is it fit for purpose? That is kind of left to individual investigators. And that's going to inevitably lead to investigator bias. So, we've developed the cohort diagnostics package over a number of years. And, like phenotype algorithms, it's never finished. It's always an iterative process. You're always trying to, evaluate how well these tools fit the data. So, first part of this is, you'll need to have an R Studio setup, and that will be as simple as following the Hades setup guide, which you can find on the Hades website. If you're not familiar with this, you should spend, as long as it takes to get this set up if you want to do it. This guide is pretty good. It goes through everything you'll need, including one thing people often miss is getting their GitHub personal access token. And if you don't do that, then you'll be limited to the number of packages you can download from GitHub. So make sure you follow this guide and set it up. And as I said before, almost all code blocks in this tutorial can be copy and pasted, so you can find this guide. We'll share the link later, but it's here if you want to type it in manually. And so then you'll want to actually set up your packages for running cohort diagnostics. And this is straightforward. You just need to install the remotes package and then install cohort generator, cohort diagnostics. For this tutorial, we're using our Odyssey web API. That's not always necessary. And then lastly, Odyssey Shiny modules, which you'll need to view the results in our Shiny app. An alternative that, if you follow this guide, is to use an RM block file. I won't go into that into details, but basically it will install the entire Hades environment at periodic, which we update periodically. So the first thing is you'll need to go and get your study definitions from Atlas. And basically what you want to do is find the identifiers. So in this study, in this guide, I've kind of put in the study phenotypes study cohort definitions manually that you can copy and paste. But you can see if you go to if you go to Atlas, you'll see the cohort definitions page. You want to find your correct cohorts, download them with the IDs. And how do you do that? Here you want to get the base URL of your Atlas instance, but with the web API reference. That probably, if you're not using the demo Atlas here, that will probably be a slightly different URL. So you might have to contact your Atlas admin to find that out. Then you just want to create a vector with the cohort IDs in question. And here, these are just the numbers we selected. And then following that, you want to use our Odyssey web API and then export cohort definition set, which will give you a nice R data frame of your cohorts. I know it's not always possible for people to have their analysis run on the same machine as they're setting up their environment for actually executing, because maybe their CDM is behind a firewall. If that's true, then you'll have to save your cohorts, and there are extra steps here that you can go through. But this is all you need if you're running a study to get your cohorts in the simplest possible way. And the reason why we do it this way a lot of the time is because of that iterative process. You'll have to re-download these cohorts and you'll have to re-import them into your R session. And the next step is obviously to just view the cohorts. Then just view them in R with the view function and make sure that the names are correct, because you could spend a long time generating the wrong cohorts and that wouldn't be very good. And you won't necessarily know until the execution starts or is running or is finished before you've made that mistake. And it's something I've done quite a lot. So it's always good to just check that your cohorts are there correctly. And then next, this is the only part of the study which you will absolutely need to figure out for yourself, and you can't just copy and paste. So here you'll be needing to set your connection details in database connector. So you want to create a connection details object, which defines the database type you're connecting to, the server, including the specific database, what port, the username and password, which I don't recommend storing in plain text like I've done in this example. We actually recommend using the keyring package, which again, if you're following through this guide, you'll be able to view how to do that. But basically, keyring lets you save any secure credentials in your system in a secure way, so you don't end up sending a script with your username and password. Please don't do that. We've had that happen before and we don't like it. So just remember to try and load your credentials in a more secure way. And then you'll need to set an ID for your database. This can be anything you like, but it's probably a good idea to set it to something that is unique to you and unique to the study or the version of your database that you're running this on. Then you'll need to set a CDM database schema, which is where your CDM lives. And this would be, you don't necessarily need to be able to write to this database schema because you're just reading, your data. So this is just your OMOP CDM. And then the last thing is your cohort database schema, which is where your results on the database server will live, and that needs to have user write permissions for the user executing this study. The data folder is just something in your local workspace. Here I've just called it results. And then incremental folder is another space, folder space in your local settings that you can use to basically run the incremental process that I mentioned before. And that basically means you won't regenerate the same cohorts again, and you won't regenerate any analysis for any cohorts that have existed. And then the next step is to go on to generate cohorts with the cohort generator package. Again, this should be fairly straightforward. If you have those settings from before, you can just copy and paste this code block. You need to set some cohort table names, which we are calling cohort, and then execute them with the generate cohort set function. So we get our cohort definition set, and then we insert data into these cohort tables. So that's the cohort table for the cohort with a subject ID, a cohort start date, and a cohort end date, and then also other tables for inclusion rule statistics and things like that that are generated throughout the process. Next, you'll want to execute cohort diagnostics. And I put this can take a long time to run, but it really varies. You know, that will depend on the size, how many patient records you've got, and you know how large the cohorts are. In this case, I don't expect it will take too long to run because we don't have many billions or too many millions of patients in the cohort. But you should be aware of that too. And again, like you can copy and paste this code block, but it's a good idea to understand what all of these settings are. I won't go into too much detail here other than the min cell count is crucial. This is what it's somewhat arbitrary in the number that you enter, but it is crucial that you're following whatever guidelines your data source provider has for setting the whether you're going to potentially risk exposing patient identifiability. So for our data sets, we normally have a min cell count of 5. Other people I know it could be up to 10, maybe even more. But that's to ensure that you can't actually, you know, say one patient has one specific rare covariate, which would allow you to potentially identify an individual within your data. And we don't want to do that. We only want to collect aggregate statistics. And cohort diagnostics is pretty strict about how data is exported so that that shouldn't happen. And then beyond that, you can decide. Thankfully, there's only one more step in this study if my browser doesn't want to respond. But that is to generate the Shiny app data after this executes. Okay, it should work now. Yeah. So sorry for that. So basically, these settings let you decide which part of cohort diagnostics to run or not run according to your study. In this study, we're running everything. If you're running a lot of cohorts, you'll almost certainly want to turn off run cohort relationship, at least in any first runs. That's just what we use to find overlap between cohorts, but it can be time consuming because you have to compute the overlap between every single pair of cohorts. So that's useful to know. And then lastly, you know, creating your results database. So this is crucial. After the execution is completed, we need to insert data into a database. Here we use SQLite, and it should just be pointing your data folder, and then you get an SQLite database path. Following that, you can launch the Shiny app, and that's just done with Launch Diagnostics Explorer. And there are a few more things you would need to know if you were sharing that, but I can leave that for future reading on your part. And beyond that, I provided a set of resources here if you want to read in more detail. And also, if you want to get in touch, you can always contact us on the Odyssey Teams, the Odyssey Forum. And if you have any issues, please post them on the GitHub issue tracker for cohort diagnostics. I try and respond to them quickly, but often I'll probably need a bit more information from you if you find a problem to find out to diagnose the issue. And without further ado, I can hand over to Azza.
So thank you, JPEG. And now you all know how to run cohort diagnostics. And just like magic, you will put the code that JPEG gave you, and it will poof, work in no time. Once it runs, and if it didn't, just talk to JPEG or Gotham or somebody to help you. But once it runs, cohort diagnostics generate a lot of data that you can then explore in our Shiny. In this case, for this study, we have ran the study cohort, our outcome, our exposures, and our indication in a bunch of databases. And then we pushed all the results on data.odyssey.org/SOS challenge phenotypes. Do not go to this URL that is available for all of you now, because sometimes with a lot of traffic, the app can get sluggish and the tutorial will not work. So wait a little after the tutorial. You're all welcome to explore the data on your own and see what you want to see. But for now, let me walk you through what you see in this Shiny app. So on the left side of the screen, you will see all the diagnostics or these tabs that the tool runs. Basically, what they are, they're a bunch of descriptives or descriptive data about the people who met your cohort definitions in the database that you ran the tool on, which allow you to explore who are these people and if they are consistent with what you expect given your target, given the clinical idea you're trying to capture in the observational data. So the first page you're going to land on is your cohort definition page. What this shows you is basically the cohort. So in this case, we have our outcome, end-stage renal disease. Now, if you remember last Tuesday's tutorial, Anna walked us through how to develop end-stage renal disease definition in Atlas, and she had two versions. She had what she called the simple definition, which allowed people to enter the cohort if they have end-stage renal disease captured in a condition or a procedure or an observation. And then she had the complex definition, which is what she called complex, which what we call here end-stage renal disease reference 1, which is allow people to enter the cohort if they meet the same criteria of the simple definition, and also allow others to enter if they also have definition, if they also met the criteria of end-stage renal disease through measurements of eGFR or a dialysis or a transplant. So the complex definition is a broader definition that has multiple entry criteria, and the simple definition is technically a subset that only allow people to enter if they have the end-stage renal disease diagnosis. Okay, we also have our exposure cohorts, the 3 different exposures that Asya walked us through Atlas. And then we have the indication cohort, which is persons with blinding disease. Keep in mind that in our exposure cohorts, everybody have to have exposed to one of these drugs and also have the indication of the blinding disease. So technically, those exposure cohort have the indication nested with them, as if you remember from Asya's tutorial. Perfect. Leave this cohort on the side. I'll talk about it in a minute. So those are the definitions that exist currently in our Shiny. So in the cohort definition app, not only you know what's in there, but you also have all the data about the cohorts that you can see in Atlas. So if you don't have Atlas or you have no idea what cohort is in here, you can explore your definition in a print-friendly way. You can look at your concept set for every definition. You have the JSON object if you want to take it and implement it somewhere in an Atlas or in your data and the SQL. So everything that is available in Atlas is also available in this Shiny if you don't have access to Atlas, to basically transport the definition, explore them, and see the logic. Okay, so that's the first page. Still not looking at evaluation, just looking what's in there. The second and the third tab are the concepts and data sources and orphan concepts. Those are basically, I'm not going to go through them today because they basically include the same kind of information that Anna showed us how to use in Phoebe. Concepts and data source is going to show you the distribution of the concepts that are included in your entry criteria and how they, the occurrence of them across the different data sources. And orphan concepts going to show you the concepts that may be related to your idea of interest, but are not included. And that's what basically Phoebe recommend for you. So you at this point should have considered that data when you developed your definition, but it's also good to have a final check one more time when you're evaluating work. For today, for time, I'm going to skip those because we already did them. The third or fourth tab is the cohort count. And this is as simple as selecting your data sources. So I'm going to select everything minus this one. And I'm going to select all the cohorts. So this allows you a drop down to allow you to select the cohorts and the data. And that's something that you're going to do in every tab. And then, so here you have all the cohorts listed on the top here to make sure that you captured what you wanted. And what you see in this table is simply the counts of the people who made it in your data sources that met your cohort definitions. Here are the cohorts and here are the data. Now you see it on the person level, and you can see it on the person level, and you can see it on the record level. Now, if you remember, for those cohorts in the study, our definitions were designed to be earliest events. So basically the person and the record are identical. For simplicity, I'm going to hit on person just to make it less stuff to look at. Okay, so what can I see? If I'm going to look can expand that, and I'm going to look at the exposures first. So on the spot, off the bat, I can see that I have those first 3 data sources, Australia, France, and Germany, have 0 exposures. So they are off the bat not eligible for our data. They're not feasible because they don't capture the exposures of interest. This is something that you may or may not have captured already in data diagnostics when Claire ran it. But this basically, once you develop these cohorts, you can check if they are captured in your databases. And here in this case, you know that those 3 databases are out. You can also see that there's another database that also have very low counts that probably would not be eligible for the study. It's very few counts in the exposure cohort. But other than that, you can see that for the exposure cohort across the other data sources, you're capturing somewhere between a couple of thousands to hundreds of thousands, which is very good for potentially your power. So that's something you can learn on the spot, and you can understand the magnitude of the people you're dealing with for the study. And you know which data sources are out off the bat. So that's for exposure. I'm going to go now for our outcome, end-stage renal disease. And as I just mentioned, you have the end-stage renal disease simple definition, and you have the complex. Remember, the simple is a subset of that complex. I have here a third definition that I put in my Shiny or in my cohort diagnostic for evaluation purposes. This is not a cohort that I want to use in the study, but this is a cohort that's going to help me evaluate my end-stage renal disease cohort. What is this cohort? So remember, I'm going to take this database just because it's simple. There are 84 people who made it through the simple definition. Basically, they have a diagnosis of end-stage renal disease. But I have 407 people who made it through the complex definition. So these are the people who made it because either they have a simple, they have the diagnosis, or have a dialysis, or have a transplant, or have a measurement that met the criteria. The 323 here are the additional people that I gained through my complex definition that do not have the diagnosis. So if you add up 323 to 84, that's the 407. So those are the marginal cohort. So those are the people who don't meet the simple cohort. They don't have the diagnosis, but they met the other criteria. So this is basically the people I gain if I went with the complex definition. Make sense? And that's useful for me for later. But what that helps you understand, just from count perspective, is what's the magnitude quantitatively of the difference between the 2 options I have here. If I go with the simple definition, for example, in Germany here, I have 13,000. If I went with complex, I'm going to add 7,000. So that gives you what are the potential addition, in this case, probably sensitivity that I gain when I broaden my definition. And that gives you an idea of what's the margin of that gain in sensitivity. You can look at it here and do the math and see how much effect I have. So clearly in those European databases, at least in Germany, in Australia, in Germany, that's a good difference. It makes a difference if you add those inclusion criteria. But if you look at other databases, for example, let me see, pick one here. This OptimiHR here, you're already picking 500,000 with a simple definition. If you add those extra inclusion criteria to help you to add more people, you're gaining about 50,000. That's about 10% addition. If all of these people are truly cases, that 10% gain in your sensitivity. If they are false cases, that are 10% loss in your specificity. Another way you can look at that is another diagnostic that gives it to you in a nicer way. That's the cohort overlap. So again here, I'll keep all the data spaces, but I'm going to select the 2 cohorts that basically they're 2 different phenotype definitions representing the same clinical idea, the 2 options I have. So what do I see here? These are the Venn diagrams of the overlap between the simple and the complex. Remember, the simple is a subset of the complex. So that means the unity of these 2 different phenotypes definitions are basically the complex one, right? Because it's the broad one. So visually here, I can see that in those European databases, the purple section is the people I'm gaining through the simple definition, and that red pink one is those additional people I gain through the complex. So clearly in those European databases, that adding that criteria is adding a lot of people. Indeed, in France, I'm capturing nobody with a diagnosis of end-stage renal disease. That can make you question, is that because no people have this diagnosis in this database, or is it that I'm missing the ICD-10 that is the source codes in France? So that's something I should go back and check, that I'm capturing codes of ICD-10 of end-stage renal disease. Make sure that I'm truly not capturing anybody, because truly nobody has those codes in France, or for some reason I missed the ICD-10. So that's a check that you need to go back to. In this case, it's truly, we're covered with the codes. It's the database doesn't have those codes, but I'm capturing people through the dialysis, transplant, and measurement. In the American database, I have a flip story. Adding those extra criteria of dialysis, transplant, and measurement is really not adding much. So you can see here, starting from here, it's only that pink bar. So it goes somewhere from 19%, 9% in OptumEHR, 7% in DOD, 7% in Premier, 19%, that's the biggest one, in CCAE, and then 4 and 5% in Medicare and Medicaid. So it matters in European databases, which I already know kind of out of the study because they don't have exposures, but it doesn't matter that much in the US databases, whether I use the complex criteria and added transplant, dialysis, and measurements. That again gives you the magnitude of the difference between the two definitions and gives you what's the potential gain in sensitivity if you added more criteria, and what's the potential loss in specificity if those people were actually false positives. Okay, I hope it's clear, but I need people to nod to at least know that. Following? Okay, perfect. Okay. So that's cohort overlap. Now I'm going to go to incidence rate. That's another diagnostics, which is going to show you the incidence rate of the cohort of the event of interest. So in this case, end-stage renal disease. Let me just pick the simple definition for simplicity. The incidence across the calendar year. So every dot in this plot is the incidence of end-stage renal disease in each calendar time that we have on the data. On the y-axis here, you see all the databases. And you see the incidence here stratified by age. Those are the age groups by 10 deciles. And you see stratified by female and male. And you can make all these selections on the top panel here, and you click on generate plot, and it generates depending on what you selected for age groups and for gender. So for example, I removed the people who don't have gender because they don't make it into the study anyways. And I removed that last year of data because usually it's unstable and incomplete. So what do I see here? So this gives you the incidence rate of end-stage renal disease. How is that useful? Well, I look what I observe. First thing I'm observing right here is that there's clearly an increase of incidence or risk of end-stage renal disease in this data source with age, that those plots are going higher with the increasing of age group. That's consistent roughly across all the databases. I also see that males are at a higher risk of females. So that green line is going on top of that red line. So if I know nothing about end-stage renal disease, what I just learned that it increases with age, the risk increases with age, and it's higher among male versus female. If I'm a clinician or epidemiologist that knows about it, I can I can check if this is correct or not. If I don't, which in my case, I just looked it up. So I found a paper here about end-stage renal disease in the US. I looked at the epidemiology section, and here is the age and sex pattern. So it tells you that the prevalence of CKD increases with age, and it's the highest among 60 and older, and the cumulative incidence is higher in males than females. So that is something that I was able to observe. Actually, if you look at those trend, they trendly the highest among those 60 and above. Those tend to be on the top. So that checks with my pattern. So that just gives me some confidence that the patterns I'm detecting here is consistent with what's known about end-stage renal disease. It gives you some confidence that you're capturing the true clinical event. I can also check the stability of the incidence over time, because generally we expect the patterns of diseases to be monotonic. If there's ups and downs, you just want to make sure that it's not related to some data capture processes. For example, in the US, we have always that problem of going from ICD-9 to ICD-10, which sometimes causes a problem with capturing the data. So you want to make sure you don't have these dips or peaks in that era. So in this case, I'm saying some patterns, for example, in Medicaid right here, but it's not huge, and just make sure that it's not something that has to do with the cohort definition. Okay, and there's a lot you can see here, but for this case, those are the things you can learn, and you just move on that it's consistent with what you expect. For time purposes, I'm going to go to the most important diagnostics, which was called here on the app cohort characterization. So what that is, this is basically a gigantic table that you can generate that gives you the distribution of every single data point, that's every single concept exists in the data among the people who met the definition in every database at different time points related to the index date. So let's see how you can do this. So first of all, you have two options. You can either create the pretty table, and that's basically what we like to call table one. That's your table one in your paper. And you select the cohort. So if you want to do your table one in the exposure cohort, that's basically the people you start to follow, you can pick any exposure. In this case, I'm going to stick to the outcome because I want to show you some characteristics about the outcome. And then, so you pick your cohort and you pick your databases. So I'm going to I made some selection just to make it simpler. You can select all the databases. It doesn't matter if you want to see it at once. So here it is giving me the characteristics that table one of the people in the end-stage renal disease across different databases. And in this case, in the pretty table, remember, it's your table one, so that's going to be on baseline. So not during follow-up, but at baseline. Okay, so I first see the age distribution, which is something I already understood from the incidence rate. And you can see here that 60 to 70 is where you have the highest proportion minus those. First, did I pick the right people? Yeah. Minus those very old people, because it said that it can really go high up among people who's really old. Okay, the gender distribution, you already know that from the incidence rate, and it's consistent. You see here a slightly higher range among male, other than this database that has a slightly different breakdown. But other than that, hold on, something is. Am I looking at it right? Let me just pick it one more time. The patterns change a little bit. Whoops. Okay, yeah, the data was not correct. Okay, this makes more sense. So here you go. You see the 60-70 have the highest proportion, which is what you expect. You see the males higher proportion than females. That's what you already know. If you have race in your data, you can see if the race pattern is also consistent. You can also see all the characteristics of the people who made it to the end-stage renal disease at baseline. So what you expect here are things of like risk factors to be highly presented. So what's the biggest risk factors for renal disease? Something like hypertension. So here you see hypertension with a certain going from 30% to 50%. You can see diabetes, which is another risk factor, to go up from 30% to 40%. You can also see something like pneumonia, which we're going to talk about, but you basically see all these diseases or risk factors that you expect among people who end up with end-stage renal disease. And you can check if this makes sense or not. In the exposure cohort, remember that we were worried about people who are using any of those exposure drugs, but some of these drugs are indicated for malignancies. So you can also check here, what's the proportion of people who have malignancies at baseline, which if you remember, ASIA put already a criteria that remove people of malignancy, so you can check if that worked. And you see here that there's still some proportion of people, something between 1.5 to 3% across the databases that has a malignant neoplasm disease. That might be the skin disease malignancies that we did not exclude on purpose. But that's, again, another check that everything you intended to do did manifest in the data as you expect. That's just your pretty table. Now let's go into what more you can do. So we're going to pick something called the raw table, and that's going to give you every distribution of every concept observed in the data at different time point. And here you can select your cohort. So let's go back to end-stage renal disease. Let's pick those databases for simplicity. You can pick them all. Temporal windows are basically the time period you want to assess the occurrences or the prevalence of the different characteristics or codes. By default, the app will select for you 4 different time periods. This is the year or the 8th month before the 11th month before index. It's going to give you a snapshot of 1 month before index. It's going to give you that date of index and the 1 month and the 1 year post index. The reason why those are selected, because those can help you understand characteristics of the people at the time, just before and just after they met the diagnosis or the criteria of end-stage renal disease. So that's kind of the proximal time you're interested in these people. You can filter the data on certain domain or certain codes, concepts, but let's select everything and hit generate, which will create the same table that was already in there. So what's going to happen? What do you see here? So one thing that you can do off the bat is just sort things and see what are these things that you are seeing happening at a higher rate or a higher proportion in the data. You can pick any data source. Let's pick DOD is my favorite. Of course, the first thing you should see, and you can filter. So in this case, I'm filtering on condition. I'm going to pick up condition occurrence. So you know what? Let me pick here. So what you can see, first of thing that you expect to see are the things that are part of your definition. So chronic kidney disease, it's the parent of end-stage kidney disease, and you're looking at it as a group. So you're looking at chronic kidney disease and all its descendants, which include end-stage kidney disease, and that's why it's 100% among everybody, because you designed it that way. You see here renal impairment. Renal impairment is one of the parents. You're also going to see it at high proportion because this is renal impairment. It's one of the parents, so it's going to wrap up to it. But if you go down a little bit, ignore all the things on the top that are part of the definition, you're going to start seeing other things like cytopenia, pain, heart disease, renal failure syndrome. That's not part of your definition, but clearly occur in a high proportion. You're going to see something like, again, essential hypertension. And you can see that it's occurring before index, on index, and the period after index. And that can, first, if you're a clinician or you have some clinical background and understand the disease, you can see, oh, are these things consistent with what I expect? Do I expect pain and diabetes and hypertension and RBC count low and things like that among people with end-stage renal disease? And that's how you check if this makes sense. If you don't have a clinical background or you know nothing about end-stage renal disease, well, we have Anna, who was very useful for us for the evaluation of our cohorts, who authored this nice clinical description that tells you what you should expect among people with end-stage renal disease. So she tells us what's the presentation, what's the diagnostic, and what's the therapy plan. Well, all of these are events that should be captured in the data. So for example, edema is one of the presentation of end-stage renal disease. I can take edema and I can put edema right here. Let's see how many of the people, what's the proportion of edema in these people. So I see a lot of edema right here. I'm capturing it on the group level, so that's edema and all its descendants. I'm also capturing it on just the condition occurrence. That's just one concept of edema. I'm capturing it before and after index. So if I take the group era of edema, that's all edema and its descendants. So I see that in that 1 year after index, it occurs somewhere between 20 to 28% among the people in these databases. On index, I see that, where did it go? On index, there are something between 6 to 14.6% of the people have reported edema on that same day. So if I compare that occurrence of edema before and after index, so I take that year before index, that's it. You can see how in that year before index, it was 1.9, it became 11.5 after index. It was 14 in this database, jumped to 28, 12 jumped to 24. That all tells you that edema as an event tend to occur higher after people were diagnosed with end-stage renal disease. That tells me that, well, maybe those people truly had end-stage renal disease. And the proportion of it is pretty considerable. Like on one date, on one code, it was reported 6 to 50%. So that's good. And you can go do this for every single event that you expect to observe for people with end-stage renal disease and assess if it's truly occurring or not. Here you see dyspnea. Again, you see a big uptake after diagnosis, but you also see some people has dyspnea before diagnosis. So here is dyspnea. You can see that there's some proportion that have it in that 1 month before diagnosis. That also can let you think, did these people already had end-stage renal disease before they have that diagnosis or not? That's index event misclassification. But the point here is that these things are occurring to a certain degree, and you see an uptick after diagnosis, which tells you that that time that they were diagnosed with end-stage renal disease is related with an uptick of the presentation of the disease. So that makes you feel good about it. And so forth. So you can do all of this. You can look at something like dialysis. I went to kidney transplant. So you see some people. Some people actually have kidney transplants before index. So what do you think of somebody who had end-stage kidney disease and had a transplant in that year before index or that month before index? Are those true cases? Are those could be? But maybe they already had end-stage renal disease before they had the transplant. So that's index event misclassification. And that maybe tells you maybe I should adjust my definition to index people, not only at the time that they have a diagnosis, but maybe at the earliest of having diagnosis or a transplant or a dialysis. So at least you are sure, or like you shift your index to the first evidence of a kidney end-stage kidney disease. And this helps you assess how much you need to do that. So are you willing to accept index event misclassification among 1 to 2% of the people? Or do you want to remove people who have transplant before end-stage kidney disease, if that's not possible? Now, of course, it might be possible. Maybe that new kidney failed. But these are all the things that you can do. So you need to have some good clinical intuition to start to assess what are you observing in the data, and if you need to make any iteration on the definition. Okay, I have 1 minute. The one thing I want to show you, the two things I want to show you in 1 minute is, remember that definition I created, which represent those marginal people. Those are the people that meet the complex definition through dialysis transplant, but do not have that diagnosis. I can now compare, that's the last diagnostic you have here, is compare characteristics. And what you can do here is plot all the covariates, every concept in the database among the people in that simple definition compared to the people that you're adding through your complex definition. So those are people who have dialysis transplant or a measurement of that meet the criteria, but do not have the diagnosis. Those are the people you're adding. And you can look at their characteristics and how compatible these people clinically are with the people who have diagnosis on index, on the day after, the month after index, on the year after index. Now, it makes sense that if you see the distribution of these covariants to be very similar, in other words, on that diagonal line, you can say, well, those are the same people clinically, so I should include everybody because they are the same people, whether they have a diagnosis or not. But if you start to see patterns where you see a slightly different distribution, which I think you see here, at least you can see much more dots happening here among people. This is your target. This is the people who have a diagnosis compared to the people who don't have a diagnosis that have a dialysis transplant and measurement. Maybe they are not the same people, and that would tell you, well, maybe those are false cases because they don't have the same clinical profile as the people that maybe I have more confidence that they truly have the end-stage renal disease. And these are things you can do. You can go dot by dot and assess what are the differences. Finally, I am at time. You can run p-evaluator, and p-evaluator can quantify for you what's the specificity, sensitivity, and PPV for the cohort. and compare. In this case, we're looking at the complex definition compared to the simple definition. You can quantify the specific sensitivity, and it's somewhere between 0.5 to somewhere between 0.8, and that's true for both definitions. And we didn't expect to have so much difference with the complex because, as you saw in US databases, you'd only add somewhere between 5 to 19% additional people. But the simple definition is making the bulk of the people you have. And you have a very good PPV, which kind of consistent with what you saw in cohort diagnostics, where you saw all these events that you expect to see, like edema, dialysis, transplant, actually occurring in the people with the disease. And that's reflected in that relatively good PPV of somewhere between 0.7 to 0.9. And that's how you evaluate your cohort. And there are more things to see, but I think I will keep it to the office hours to see more stuff that we saw in this definition.